Hello everyone, my name is Chakkrit Tantithamthavorn. I am a senior lecturer in software engineering at Monash University. Today, I am going to present the paper titled An Empirical Study of Model-Agnostic Techniques for Defect Prediction Models. As everyone knows that software defects are very costly and prevalent, but they are very hard to predict and to prevent. So practitioners want to find and fix defects as early as possible instead of fixing them in productions. That's why SQA practices like exploratory testing or code review have been adopted in many software organizations. But such activities are still very time-consuming and very expensive. So let's imagine that you work at Google with millions lines of code. You just have no idea which files are likely to be defective in the future. And developers cannot efficiently and effectively find the highest numbers of defects given the limited time and resources. To address this problem, defect prediction models have been proposed to help developers prioritize their limited SQA resources on the most risky files. So defect models are an AI or machine learning model to predict which files are likely to be defective in the future. And in general, we start from preparing a training dataset or defect dataset, then we build a model. For a given file of interest, we input this file into the defect model to understand the prediction whether a file will be defective in the future or not. However, such AI or machine learning based defect prediction models are still very complex and often treated as black box. For example, deep learnings often have millions of learned parameters, random forests often have thousands of trees, so they are very hard to understand how does it work inside. When we talk to practitioners, they often ask questions like, why this file is predicted as defective? Why not clean? Why this file is predicted as defective? Why another file is predicted as clean? So a lack of explainability of defect models often lead to a lack of trust in the predictions. And this poses a critical challenge to the adoption of defect models in practice. So finally, practitioners might just say no to the defect models and don't use it. Thus, prior studies often used model interpretation techniques like ANOVA or for regression models or variable importance for random forest model to better understand what factors are the most important. However, this is not enough. Such global explanations are quite generic and they are often derived based on training dataset. They are not specific to the individual prediction of the instance to be explained. To address this challenge, this paper is the first to adopt model-agnostic techniques from the explainable AI domain to explain the predictions of defect models. And such explanations will provide extra information to practitioners so they can understand why a machine makes that kind of predictions, or developers can make a better data-informed decisions whether they should trust the predictions of defect models or not. LAM is one of the state-of-the-art model-agnostic techniques, which is published at KDD 2016. To date, this technique has been widely used in many domains with more than 5,000 citations, but still have been rarely explored in software engineering. The goal of the LAM model-agnostic technique is to build a local interpretable model that mimics the predictions of the global models. So, given an instance to be explained and a global defect model, LAM performs the following step. First, LAM generates synthetic samples around the neighborhood, and then LAM will build a local interpretable model or K-lasso model for our case to locally approximate the predictions of the underlying global model. And then LAM will generate an explanation by extracting which features are most important to the individual prediction of the instance to be explained. Prior studies argue that explanations should be presented as answers to why questions. Now, I will show how LAM can be used to generate a contrastive explanation to answer many why questions. So let's take a look at an example visual explanation here generated by LAM. We apply LAM to explain the predictions of this file, notifybuilder.java from the Camel project. And the global model predicts this file to be defective with a probability of 74%. And in this example, the blue bars indicate the supporting score or the factors that support the predictions, while the red bars indicate the contradicting score or the factors that contradict the prediction. So first, we can use LAM to answer a plain fact. Why is this file predicted as defective? So we use the LAM support explanation to answer this question. For this one, it shows that this file is predicted as defective because of having the numbers of class couple greater than 5. So it implies that developers should consider reducing the numbers of class couple to mitigate the risk of having defects. Second, we're going to use LAM to understand the property contrast, or why is this file predicted as defective rather than clean. So we're going to use the LAM contradict explanation to answer this question. For this one, it shows that this file is not predicted as clean because of having the numbers of developer less than 2. Therefore, it implies that developers should consider maintaining the numbers of developer less than or equal to 2. Third, we can also use LAM to understand the time contrast explanation as well. If we apply LAM to the predictions of the same file but in different releases, we can also better understand why this file predicted as defective in the release 1 but predicted as clean in the release number 2. Finally, we can use LAM to understand the object contrast as well. Given the same releases but different files, we can use LAM to explain why is file A predicted as defective, why file B is predicted as clean. So there are so many potential usage scenarios when using expandable AI techniques to address the software engineering problems to discover knowledge. However, little is known about how well when such tools be used for expanding the predictions of defect models. In this paper, we set out to investigate 6 research questions. We're going to present one by one as follows. For the first research questions, we asked how well can we improve the accuracies of the LAM local models. Because LAM actually has so many hyperparameter settings, we want to know whether such parameters have an impact on the on the accuracies of the local models or not. And what we found is that when we optimize the hyperparameter settings of LAM, we can improve the local goodness of fit measured in terms of R² by on average 8%. And then we also investigate, do different predictions have different explanations or not? The intuition is that normally global explanation is too generic. It's like one model, we get one explanation, but they are not individually explain the predictions of the unseen data. So we want to investigate whether they are different or not. And what we found is that given the same defect models, different predictions actually have different local explanation. This finding actually highlights the need of the expandable AI tools for software engineering, and we should focus more on the local explanations instead of relying on the global explanations. Third, we asked, are local explanations overlap with the global explanations or not? So the key intuition is that ideally local models should accurately mimic the predictions of the global model. So what we find is that top 10 features of the local explanations are mostly overlapping with the global model, but they are not the same at all. So we kind of say that we kind of understand that most of the local explanations are in line with the global, but they are not the same. And fourth, we ask about are model-agnostic techniques rely on random seed or not? So LAM actually involves lots of randomization, generate the synthetic samples. So we want to know whether there is an impact with the random seeds or not. So what we find is that yes, random seeds need to be defined to increase the stability of the model-agnostic techniques. And the research question 5, we want to investigate as well how fast it is. So LAM may incur overhead when we adopt in practice, but we still don't know how slow they are. So what we found is that LAM is crazily fast for defect models. Finally, when we generate lots of visual explanations, we want to investigate as well how do practitioners perceive with the visual explanations generated by these techniques, right? So what we found is that 65% of the participants agree that explanations are insightful and useful. So these results lead us to conclude that XAI tools are needed, they are insightful, they are fast, and they are perceived as useful by practitioners for explaining the predictions of defect models. So now we're going to call for a new research topic. Is in the areas of expandable AI for software engineering. I think the key question is that how can we make software analytics for other tasks, other SE tasks more expandable and more actionable as well? If you would like to learn more about this area, please see our XAI for SE book. Thank you so much.
Okay, welcome to the second paper of this session on defect prediction and bug characterization. And I'm very happy to have two of the authors here, Chakkrit and Jirayus. Sorry for my pronunciation. And the paper is a TSE paper on an empirical study of model-agnostic techniques for defect prediction modeling. And I'm happy to report that earlier today I was in another session with some work on explainable AI, and then there were a lot of questions from the audience. So we're hoping for this audience too. Please post your questions in the chat, and I will try to discuss them with the authors here. I can start with something of my own to get things going. So you say here in this paper that the explanations provided by these explainable AI model-agnostic techniques, they do overlap with what the global model that they are sort of refining their explanation of is saying. So can you say a little bit more about what is this overlap and what is the added value of the explainable AI technologies?
Jirayus, do you want to start?
Okay, sure. So we found that the explanation that are overlap but they are not actually the same. So for example, when we look at two different files and look at their instant explanation, they are actually varied. But when you aggregate these results at the high level, so for example, feature complexity and size may appear as the top rank matrix, but they may not appear at the same rank when looking at different instances. That's why this adds some values, because each file may have different characteristics of defective.
Yeah. Yes. And of course, that's what you expect, right? I mean, you expect that on average, the global model, that's what it's doing, right? It's capturing the overall behavior. So in that sense, it's good. So now we have a question from Aurora here in the chat, and she really liked your presentation. Based on your experience with Lime, so this is one of the most used techniques in this space, I guess, how accurate is the synthetic generation of the instances? So basically the explanations that Lime generates, are they accurate?
Okay.
Do you want me to?
Anything is okay.
Okay, so well, this is basically one of the limitations of LAM is that LAM use random perturbation to generate these synthetic instances. So therefore, these instances, these randomly generated instances may not reflect to the original distribution of the original dataset, and may sometimes appear like not possible in practice.
Yeah.
Yes.
So I think LAM still has a limitation on that. So that's why it is still an open question, and we still need more researchers to address this kind of problem. So I just want to convince everyone to work on this area.
Yes. I'm sure many will, because it's very important for practitioners, right? But yeah, so I think you answered also the second part of Aurora's question there. Because yeah, so basically the answer is that synthetic generation with Lime at least has the limitation that it can generate something that cannot even happen in practice, because it doesn't have those constraints. It doesn't know about those constraints, right? So we have one question from Fahad. Does a change in the model features have an effect on the performance of your approach? So I'm not really sure what the change would be, but yeah, maybe you can discuss it a little bit.
Change in model features.
I think change in the model features, maybe I should interpret as a like feature permutation have an effect on the performance of your approach. I'm not quite sure.
Yeah.
Maybe Fahad can clarify a little bit.
Yeah, maybe you can clarify, Fahad, because it's not clear to me either. I guess one thing we can say is that, of course, if you take away features, you have less information, then of course the model cannot really I mean, it must decrease in accuracy or performance at some point, right? Because there's less information. So from an information theoretic perspective, that must probably be true. And this would mean that LIME explanations in some sense will also have to be a little bit worse if you strip out a lot of features, of course. But I guess in general, it should be, I mean, it's general. It's not, it can be applied to any type of model. So from that perspective, I guess it's fairly flexible. So Fahad, maybe you can clarify there. Aurora is saying she will read the book. Okay, good.
Thank you.
So you also try different explainable AI techniques, I think, right? So did you see some clear benefits in what they provide somehow?
Oh, yes, I think, of course. So in this paper, we actually try to propose, we talk about the theories of the explanation. We come up with different types of explanation, the contrastive explanation, that kind of thing, P-contrast, T-contrast. So in the presentation, we already show how LIME can be used to generate the explanation and answer different types of questions as well. I think the next step for this area is that how can we use LIME to discover new knowledge in like the MSR types of paper. Normally, we just have one research question, what is the most important features, blah, blah, blah. But that kind of research question, we just derive like a generic insight from the global level, the model level, but not specific to this one. Have we thought about how can we, like one new research question, whether we can trust the model or not by using LIME to actually explain whether the explanation makes sense or not, that kind of thing. For example, if we use image classification, try to classify dog and cat, but use background as the most important features, it doesn't make any sense at all. So same to this one. So I think, so explainable AI for SE is still in the early stage. Yeah. So I think we have lots of things to do more in this area.
So Fahad is I have a question on what kind of features did you actually include?
Okay, so we use in total 65 software metrics, vary from process metrics like what is that? The numbers of add lines, numbers of delete lines, the code owner, numbers of major developers, numbers of minor developers, the expertise of the developers, and we also look into the product metrics as well, lines of code, psychometric complexity, and a lot. Yeah.
And I guess it's often the well-known ones, like size is of course always important and so on, right?
Right.
Yeah. Did you have any organizational metrics? I guess not. It's code-based.
Code-based, yes. But we incorporate some human factor as well, like the code ownership, the numbers of major developers, minor developers. Yeah.
Have you seen any patterns yet in what practitioners prefer in the explanations? Is there some type of explanation that they seem to like more?
Jirayus, maybe you can answer. Yeah.
Yes, actually, in one of our RQ, we conduct a survey and ask them like what types of contrastive explanation do they want, and they said that well, basically, the P contrast, O contrast, T and T contrast, they can answer the why questions and build trust in the prediction models. But among these three, they prefer the I think it's T contrast more than the others.
Okay.
Very nice. The explanation of the same file in version 1 comparing to the same file in version 2.
Yeah, so basically, like why this file in the previous release predict as bug, but now predict as clean? Why is that? So they want to investigate further. Yeah.
Like a differential
knowledge is very beneficial to developers. Yeah.
Okay. Thank you very much. Interesting work, and we hope to see follow-ups by many groups and yours too, of course. Thank you very much.
Thank you.